Welcome to the Stanford CS224W course. Today I will be your guest instructor on behalf of Jure. My name is Jiaxuan, and you might find more information on myself on the website. I also was one of the head TA in the previous offering, and so I'm relatively familiar with the course. Today I'll be very excited to give the topic of graph neural network to you all in this lecture. So let's give a quick recap of what I learned in the previous lecture. So the key concept we learned is node embedding. Our intuition is that we want to encode nodes in the network into a low-dimensional vector space. In particular, we want to learn a function that takes an input graph and embed that into low-dimensional node embedding space. Here we project it into 2 dimensions. And the key problem of machine learning on graph is how do we define this function f? So here's a recap of how to encode a node. We have the goal is to define a similarity function that can represent the similarity in the network, and we want to approximate in the embedding space. And we really need to define 2 things. The first is the similarity function, represent how 2 nodes are close together in the network. Another thing is the encoder function that basically tells us how to map the node in the graph into the embedding space. And there are 2 key components here. We have encoder that map the node into embedding, and decoder that define this similarity function. So the encoder function will take the node as input and generate embedding in the d-dimensional space. And similarity function will specify the relationship in the network and also express into loss function as a decoder. And how do we define the similarity? Last lecture we talked about random walk-based similarity function. For example, suppose 2 nodes, they co-occur in a short random walk, then we think these 2 nodes are similar. So that's one way to define similarity, and we can also come up with other way to define similarity. And how about encoding? We have seen one of the simplest way to encode a node, that is through shallow encoder or embedding lookup. So in this shallow encoder, we have embedding matrix, and one column of the embedding matrix represents 1 node, and the dimension of the embedding matrix represents the size of the node embedding. And we talk about embedding lookup, which means that we'll to represent the node, we will pick 1 column in the embedding matrix and get that vector as the node representation. So this is the shallow encoder idea. So what are the issues of this shallow encoder? Well, we list 3 key limitations. The first is that this way of encoding nodes is not really scalable because we assign 1 learnable vector for each node. So in total, there will be to the order of v times d, this large number of parameters. And it wouldn't work for a real-world large graph, say it has billions of nodes. And another limitation is that this approach is transductive, which means that the encoder can only apply to the nodes that have seen during training time. So suppose we have this embedding matrix, but there's a new node that comes. We do not know how to encode that new node because it's not even in the embedding matrix. And lastly, this approach does not incorporate node attributes. So in real-world graph, the attributes on nodes are usually very valuable. For example, in protein interaction graphs, we have a lot of protein properties that can be associated with a given node. So without that attributes, we wouldn't be able to meaningfully learn from a network. But this kind of encoding embedding lookup, we wouldn't be able to utilize such valuable attributes. So these are the limitations for shallow encoder. And that's why today we want to dive deeper into how we can design more expressive, more powerful encoders. And our idea is to use deep graph encoder. And the idea is that rather than using a simple embedding lookup, we will define multiple layers of neural network transformations and use that deep neural network to encode a node in the graph. And note that these deep encoders can be combined with the node similarity function that we have just introduced. For example, we can also define some sort of random walk-based similarity function even for the deep encoder that we will later introduce today. So here is our plan, the pipeline of how to encode a deep graph encoder. So our input will be a complex network. We'll pass it through several graph convolutional layers. Between these layers, we can inject, for example, activation functions and then some regularization layers. And after computing this through this deep encoder, we will get output. The output could be node embeddings, which we most commonly seen, but we can also generate, say, embeddings for subgraph and even embedding for entire graphs. So these are some options that we can use to generate through this deep graph encoder. So suppose we have this encoder, what we can do? Well, we can define many exciting tasks on graphs, and here I list 4 different levels. On the node level, we can use this idea to encode different nodes and make node classification. For example, suppose we have a drug-protein interaction network, and then we can predict whether this drug is toxic or not, or whether it can be used to treat a given disease. We can also define link prediction on network, and link prediction can be quite useful for, say, recommender systems, where we can define an interaction network between users and items, and we can predict whether a user will buy a certain item. And we can also define community detection on our network. And this can be useful, say, for financial networks, where we can have a cluster of fraudsters, and they may have some fishy transactions between each other. And our goal is to detect those kind of anomaly clusters in the network. And finally, we can define a network similarity task. In that case, it will be a graph-level task or a graph-level prediction. For example, we can use this idea to encode different drug molecules. So here we treat a molecule as a network, and we want to classify different types of molecules. So this is just like a glimpse of different ways you can define machine learning tasks on graphs. Okay, so far we have motivated you that why we want to use deep encoders to encode graph. And we'll start by just taking a very brief introduction of basics of deep learning. And a lot of the course materials are also posted online. In this lecture, we wouldn't cover all of them. So because we assume that most of you already have some idea of deep learning. But if you feel not like very confident of some of the materials, please take a look on the website. And also we have this recitation and also office hours. So you can also ask TAs about specific questions about deep learning basics. So here I will just summarize some of the key ideas that we probably want to use in today's lecture. So our idea is to formulate machine learning as an optimization problem. This optimization problem has an input X, and the goal is to predict the label Y. And the input X can be different data modalities such as vectors, sequences, matrices, and today we'll talk about graphs. And we'll formulate this task as an optimization problem. And the problem looks like this. Our goal is to find a optimal parameter theta such that it can minimize the loss function. The loss function will involve labels and predictions. And theta is just a parameter that we want to learn, and it could be the weight matrices in a deep neural network. And also in this shallow encoder example, the theta is like the entire embedding matrix that we learn over. And we can also define different type of loss function depending on the type of task we care about. For example, for regression tasks, we usually use L2 loss and shown here. And for classification tasks, we also use like a cross entropy loss here. So one useful resource is this link of PyTorch, which give both theoretical and concrete implementation examples of a bunch of useful loss functions for deep learning. So we suggest you to take a look, and this will also be useful for your collab and potential course project. And another concept will usually pop up in the lecture, and we'll just use the acronym MLP. So MLP is really multi-layer perceptron, and it usually can be written as this. So we have the input X. The upper L means that we consider the input for the L layer of the network. We'll apply a linear transformation for the input, and then plus the bias, which is also trainable. we'll apply some nonlinear activation function, which could be ReLU or sigmoid, and then we get the output. So this layer is pretty simple, but it's really the building block for tons of useful deep learning architectures. For example, in graph neural network, and also even in other domains like even transformer, we have MLP to do the linear or nonlinear projections, etc. And here's a concrete example. Suppose we have a two-dimensional input to an MLP. You see there are two neurons here. We will apply a different intermediate layer in the MLP. For example, a three-dimensional, like a hidden layer here, and the output will be one dimension. So this is like a very frequently used like a module in deep learning architectures. And to summarize, we formulate machine learning as an optimization problem about finding the optimum theta for a deep neural network. And F can be anything, can be a linear layer MLP or a complex graph neural network. The way we will train it is through propagation, where we first forward propagate to make inference, to make predictions, and then we perform back propagate to optimize and find the optimum theta. And we'll use stochastic gradient descent to optimize theta over many iterations. And yeah, that's the basic idea of deep learning. So let's jump into a more exciting topic today, that is about deep learning for graphs. How can we define that paradigm, but particularly for graph structured data? So here's our plan, or the summary of our content. We'll have two major steps to define a full deep learning on graph network. We'll first consider the local network structure, where we'll describe the aggregation function, which tells us how we summarize information about the local neighborhood of a node. And then we'll define the concrete computational graph to execute the computation. And having defined this setup, we'll specify a concrete computable architecture, which involves multiple layers. And also we'll talk about how do we train this model and how find some examples about unsupervised and supervised learning on this deep graph learning network. So let's begin with the setup. We assume that we are provided with a graph as the input to this deep graph learning model. Graph can be defined as follows. We have V as the vertex set and A as the adjacency matrix. We assume adjacency matrix is usually binary. And X is the matrix of node feature. We have like the cardinality of V, which is number of node, times D as the two dimensions. D is the feature dimension of the input. V represents a small, lowercase v is a node in the node or vertex set. And the neighborhood function of V defines the set of direct neighbors of a given node in the graph. A very useful like an attribute is we have node features associated nodes. So we don't just plainly have nodes in the network. We also associate a lot of meaningful features for a given node. For example, in social network, we can associate user profile, images of a product, those kind of attributes associated with nodes. And for biological networks, we can use gene expression profile, some gene function information, etc. A lot of useful attributes as well. And you can also imagine there are cases where we don't have node feature in the graph dataset. Either they are missing or we simply don't know about them. So there are also ways to deal with that kind of failure cases. In that way, either we can use an indicator vector, for example, one hot encoding of node. So suppose we have 5 nodes in the graph, we can have a 5-dimensional one hot encoding, label the nodes as 1, 2, 3, 4, 5. That way we can get some initialization or initial feature encoding. We can also consider using constant as node feature. In that case, we'll just use a constant 1 for all the nodes in the network, just showing that all the nodes are treated equally and they don't really carry too much additional information. So these are the ways, suppose you don't have node feature in the graph dataset. So after introducing this question?
Can you go back one slide? So in the case of like vector of constant, how do you decide what the dimension should be for the...
Yeah, good question. So the question is, suppose we don't know node feature and we want to impute. We want to insert this like a constant vector here. What is the dimension? I think essentially having a one-dimensional or basic scalar is sufficient here because it really doesn't carry much meaning here, and the only purpose we want to have this feature is that it can be easily processed by a neural network, and a constant 1 means that all the nodes are treated equally. So you can imagine you can assign different value to nodes, but that can kind of carry some additional prior information. So let's say, like given a network, we can assign A and B with different values. So that basically means you could differentiate these two nodes in the network. So this like initialization means how you will treat or value different nodes in the graph. Question?
So how do we incorporate edge feature in the training?
Yeah, great question. So in this setup, we kind of simplify the case where we do not explicitly have edge features. So we say we assume the adjacency matrix is binary, but you can also imagine there are meaningful edge features. For example, we have user-item interaction graph. User may click an item, they may buy, purchase an item, so there are different edge types. In that case, we can expand the adjacency matrix. So rather than making it to be binary, we can make it like a more meaningful. For example, can be like a categorical value, where different values means different type of edges. So that's one way you can extend to edge attributes. Okay. Any more questions? Okay. So this is like the setup for graph deep learning, and let's see. Suppose we don't learn, we haven't learned this lecture, and what you may consider to learn from a graph using deep learning. Well, the most straightforward way to consider is because we have an adjacency matrix, we have a node feature matrix, so it will be natural that we can concatenate these two matrices together, and then we can apply the simplest deep learning method, which is MLP, which is introduced, and we throw this like a concatenated matrix of a graph into an MLP and see how it will predict. So this pattern can be implemented, and it may work in certain cases, but there are some notable issues. First is that this approach is not really scalable because you can see the input dimension is to the order of number of nodes, and we also have additional feature dimension D. So the the complexity here is to the order of V times D. And also this kind of approach is not really applicable to graphs with different sizes because the input dimension will vary based on the number of nodes. So if you train a network on 5-node graph, and you couldn't really apply the same network to a 6-node graph. So this is also kind of limiting. And finally, that approach is very sensitive to node ordering. So suppose we have the same network, but we reorder the nodes. So instead of calling it A to E, we may say call it E to A. And all the values here will be shuffled as well. And you can see in that case, the output will be different. So these are kind of limitations tell us we couldn't directly define a graph learning method based on the standard deep learning block. Rather that we need to define a specific architecture for graph data. Another thing we may consider in our toolbox is convolutional neural network. Because you see, for convolutional network, you can easily process imagery data. And in fact, in all the lecture materials, we visualize a graph as an image. So it will be naturally to see that we can like a pad or like a downsample the graph into the 2D space and then use CNN to process the graph data. And actually in the early days in deep learning, researchers have done that. And it actually works in some cases, for example, molecular classification, those kind of tasks where graphs are relatively simple. But the issue is the network doesn't have the regular structure as images. So you can see that network could be very complex in its structure, and most notably, it doesn't have the fixed notion of locality in this case. So what I mean is that, for example, here you may think these two nodes are close together, or these two nodes are close together. But in reality, maybe the nodes that are far away, they are also very close together with the node here because they are connected. So you have tons of options about how to visualize a network into an image. So that gives you a lot of freedom, but also prevent a model to meaningfully learn from network. And also, graph is permutation invariant because graph is an unordered object. So even though you have this like a convolutional filter patched here, you may arbitrarily shuffle the order of the node, and the meaning doesn't change, but the CNN network will treat it differently. So this is kind of like a thought experiment that shows why we couldn't directly apply CNN on graphs. So let's discuss what are the properties we really need for deep learning methods for graph. Let's start with the first property, that is so-called permutation invariance. The idea of permutation invariance is that we know that graph does not have a canonical ordering, and we can have arbitrary order plans for a given network. Here's a concrete example. We can have this network as a running example. We define a specific node ordering here, and we can define the corresponding node features and the adjacency matrix, basically describe how this graph looks like. And in the meantime, we can shuffle the order of the node here. So we can come with a second way to order the graph. And you see that after this shuffling or permutation, the node feature matrix and the adjacency matrix, they get different. And our idea is that because we know these two order plans describe the same network, what we wish to say is that the graph and node representations for these two order plans, but for the same network, they should be same. They should be identical. So this is kind of our goal when we want to define a deep learning method for graphs. So let's describe this permutation invariance property more rigorously. So what do we mean by the graph representation are the same? So we can define like a projection function or embedding function f that takes the adjacency matrix A and the node feature matrix X. And what we say is that we can have two different order plans for the network, A1, X1, and A2, X2. And suppose we take this input to the same encoding function f, we want the output to be the same. So that basically says, suppose we have two ordering of the same network, we want a encoding function f, which is, say, a graph neural network, should always generate the same representation for the same graph. This is like a visually say, like the two order plans, the output f should be the same. And we also formally define it here, that basically for permutation invariance, we not only for two ordering, like order plan A and order plan B, we should consider any potential order plan I and J. And we formally say that suppose it's permutation invariant, then for any pair of I and J, the output should be the same. We can also view this as in the matrix form. So we define a graph function that essentially map node feature matrix R into the order of V times M, and the adjacency matrix to a vector space. And we say this function f is permutation invariant if we wrote in the matrix form A and X as the input, and would permute the adjacency matrix and permute the feature matrix, and the output are the same for any permutation P, then we say this function is permutation invariant. So the same thing, we can express it in different ways, but this is a kind of definition of permutation invariance. Another concept here is permutation equivariance. So here is a different term with invariance. We talk about the idea of equivariance. So what does it mean? We talk about we can encode a graph into a graph representation where we have one vector for the graph. Now we are considering the representation in the node level. So instead of having one vector, we will have one vector for each node in the graph. And in the end, we will have an embedding or output matrix for the network. So now the output, instead of being a vector, it will be a matrix. So what is the nice property we wish to see here? Well, we get the same network, and we permute the order of the nodes. Therefore, we would like to see that the values or the encoded values for different nodes, they should be the same. But the order should be according to the position of the node in the network. Here is a illustrative example. So let's say we care about this yellow node. And in the first order plan, the yellow node is labeled as A, and it appeared here. And our hope is that because we only shuffle the order of the node, so the encoding of the yellow node should be the same. And it should appear in the latest encoding of the second order plan, E. So it says that the encoding for a node should stay the same, and it's only based on how the node is labeled. It should be always associated with the node label A and node label E. And the same is for all the other nodes in the network. Let's see another example. For example, for the green node, here it is labeled as C, and here it is labeled as D. And suppose we have this nice equivariance property, then after we shuffle the node ordering, the value should stay the same, and it is closely tied to the label of the node. We can also formally define what is permutation equivariant. That basically says if the output vector of a node at the same position in the graph remain unchanged for any permutation, and we say this function is permutation equivariant. And we can also see this in the matrix form. So now we define, instead of a graph function, we define a node function that encodes a network into a matrix instead of the single vector. And this matrix is permutation equivariant. This function is permutation equivariant if we permute input of adjacency matrix, of node feature matrix, and the output matrix is also permuted accordingly with the permutation matrix P. In that case, we say this function is permutation equivariance. So we talk about these two properties. It would be nice to review them and compare these two properties. So here I show the definition, the matrix definition of invariant and equivariant. In plain language, what does it really mean is that, so suppose we permute the input, then the output will always stay the same. This is for permutation invariant. And the output here is usually a vector. So we assign one vector for one graph. And we can also define a plain language definition for equivariant, where if we permute the input, the output will also get permuted accordingly. And in that case, this is usually considered a case where we map a graph into a matrix, and the matrix talk about the embedding vector for each of the node. And here are three concrete examples of what functions are invariant and what functions are equivariant. The first example is this, like a one vector transpose times x. It's basically a summation over a matrix over different rows. And in that case, you can easily see the function is permutation invariant because it is summation. So no matter how you permute the input x, the output will stay the same. Here's another example, which is permutation equivariant, which is pretty simple. So we just always output the node input x. This is basically the shallow encoder that we see, right? We have an encoder matrix, and essentially it's the output. And it's easy to see it's equivariant because if you permute the input, of course the output gets permuted equivalently. And finally, we have example of this a times x as a permutation equivariant function. And here we use the property of that. Suppose you transpose a matrix and then transpose it with its, and then times with its transpose, you'll cancel out into an identity function. And you see this function is also permutation equivariant. And this idea of a times x is like a simplest version of graph learning or like graph message aggregation. And we'll talk about this later as well. So any questions here? I know the concept is a bit dense here.
What is P exactly?
Yeah, so we have
it's like permutation, but like what does it look like?
We didn't have a visualization here, but it's really like a binary matrix. It has 0, has 1s, and it basically said how we shuffle different columns of a network, of a matrix, sorry. Right. Let's see. Suppose we have a matrix of 6 rows, then the permutation matrix will also be 6 by 6. And different locations of 1 and 0 says where we should put the input A to the output. So let's say if we have like a 0, 1, 1, 0, then that means we'll shuffle A and B. So like this is the idea of permutation matrix, and you can also search on the web for more. Yeah. Any other questions? Okay, we can continue. So why do we want to study these two properties, invariance and equivariance? That is because these properties are pretty important and essentially the key building blocks for graph learning method. So I show an example of graph learning method here, and you can see that it usually involves multiple permutation equivalent layers and permutation invariant layers. And this is kind of how we make sure graph deep learning method can faithfully represent the graph rather than like a method up, like an MLP that we introduced earlier. And here's like a visual example, like why MLP doesn't satisfy this property. So suppose we have an MLP, and then we have this vector as input, and we permute the values of this vector, you see. And after throwing it into an MLP, then it's clear that the output will be different because it doesn't really have the way to, say, aggregate it in a permutation invariant way. So the output will always be different. And this is precisely why this naive MLP approach to try to encode a network would fail, because it doesn't have this nice property of permutation invariant. Next, I'm going to talk about how do we specifically define a graph neural network with these two properties. And in particular, we'll talk about passing and message information on the neighbors. Question?
Sorry, can you go to the previous slide?
Mm-hmm.
So, I mean, it feels like this is a problem that would come up for, like, trying to create a neural network for any kind of unstructured data, right? Where, like, order is not important. So, like, is graph neural networks the first time it came up, or, like, was it seen before?
Mm-hmm. Yeah, that's a good question. So, the question is about, like, can we use the graph learning method to encode other unordered objects, and where this idea originated from? And yeah, I think the idea of graph learning methods, as we also dive into detail later, is inspired from learning from a set. So essentially, a neighbor, the set of neighbors of a given node is a set. And suppose we have a method to learn from set, essentially we can build like a complete graph learning method. So it definitely also have roots in other areas of deep learning. Okay, let's continue with our discussion. So far we have talked about the motivation of graph deep learning and the required properties that we wish to see in the graph deep learning method. Next, I'm going to talk a concrete example that is so-called graph convolutional networks. And this is arguably the most popular way to encode a graph and the most popular way to implement a graph neural network. So here's the idea of a graph convolutional neural network. Our idea is to encode a node based on its neighborhood structure. And we follow a two-step process. Suppose we want to encode a node I in the network. We will first define its computational graph based on the node's local neighborhood structure. So we will define it based on its one-hop neighbors and the neighbors of neighbors and so on. Suppose we have multiple layers. And then having defined this computational graph, we will propagate and transform information based on the defined computational graph. And the key concept here is that how we can learn and propagate information across the network defined by the node neighborhood structure. So we will introduce the idea through a running example. This is an input graph, and our goal is to encode this yellow node A. Based on the idea I just described, we will enroll the computational graph by finding the A's direct neighbors in the network, B, C, and D. And then we'll iteratively enroll the neighbor structure for each of its neighbor. So for node B, we will see its neighbors A and C. For node C, we see its neighbors, and so on. So you can imagine this enrolling can happen iteratively until you reach the number of rounds you wish to see. That is the number of layers in the network. And another thing to note is that a node can appear multiple times in this computational graph. What do I mean? That you can see node A, it will also appear here, like A 3 times. The interpretation here is that node A is a two-hop neighbor of itself. So if you look 2 hops away for a given node, you will encounter the node itself again. So it is allowed that we can have this duplicate value in the computational graph. So having defined the architecture of the computation, how do we really implement? We have these different gray boxes, which are essentially a neural network. What does this neural network do is to compress or condense the information about a set of different nodes, and then we'll generate the new representation and then compress it again. So this is where a neural network will help for a graph learning method in GNN. And we can repeat this process and define the computation graph for each node in the network. So we'll talk about this yellow node, but you see we can define the computation graph for each node in the graph. And the intuition here is that different nodes will have a different computation graph because their local neighborhood structure are different. And this is precisely how graph learning methods can differentiate nodes in the network. Because they have a different neighborhood structure, we'll define different computational graph, and therefore the embedding we generate for different nodes are also different. Question?
Is it true the statement that, let's say, for a problem of node embedding, that the higher the degree is, the more complicated the embedding would be? Meaning that like nodes that don't have a lot of neighbors are more easily to embed, because we see here the embedding basically scales with the neighbors, right? So if there's one neighbor, it's an easy embedding. If we have 1,000 neighbors, it's like to embed all that information from one node is a lot.
Yeah, that's a great question. I think your question is how about is a node with fewer neighbors easier to encode? Well, I think rigorously we will need to define what does easy mean, but I think intuitively, a node with fewer neighbors, it takes fewer information and it will be more easily to be compressed. And there's actually a frontier of GNN that describes this problem called so-called the over-scratching problem, because you can see that for GNN it's always a talk about how to scratch information together, and that problem definitely basically said, suppose a network is very deep and the degree of a node is very high, the network may tend to over-scratch this information of the network. And your intuition here is correct in the sense that if the node has fewer neighbors, then it's easier to get the embedding. Let's continue. And another concept here is the number of layers. In my example here, we have a 2-layer graph neural network, which basically said we look at the neighbors and then the neighbors of neighbors. And this concept is quite important for GNN because the number of layers of GNN really tells about how far away we look in the network. So given a 2-layer GNN, we'll usually be able to see the nodes that are 2 hops away. So this is kind of different with other deep learning architecture. Say in convolutional neural network, the number of layers is usually just a hyperparameter, right? You can pick whenever the model is performing the best. But for GNN, it has a concrete physical meaning. The number of GNN layers tells us how far away you can see in the network. And usually, we will pick the number of layers approximately equal to the diameter of the graph. So in this graph, we have diameter 2, which means that 2 nodes can at most have a distance of 2 for any pair of nodes in the network. So in this case, usually having a 2-layer GNN will be sufficient for the network to pick up the essential information in the network. So setting the, we can have this kind of a more principled way to set number of layers for a graph neural network. And we also have the concept of neighborhood aggregation, which is done by this gray brackets in the example.